Okay guys, here is a short video explaining conjugated diene addition. Let's take a quick trip back to Orgo 1 when we first started learning about addition reactions. The simple explanation is that you start with a pi bond, you react it with some reagent, in this case we're going to use HCl, and then you're going to replace the pi bond with two groups, specifically an H and a Cl in this case. The first step is going to be a proton transfer, generating a carbocation, and the next step is going to be a nucleophilic attack by the chlorine. Now fortunately, we don't need to spend any time going back over terms such as Markovnikov or anti-Markovnikov because they really won't apply with our first example. The mechanism here with this molecule that we're going to call 2-methyl-1,3-butadiene will be almost identical, except now we have two bonds to do an addition reaction with instead of just one. So we'll start with this one right here. So we're going to take this pi bond and we're going to react it with this H. Halogens can only ever be attached to one thing at a time, so this chlorine is going to pop off like this. And we're gonna, we kind of have two choices as far as where that carbocation forms. It can either form over here on carbon 4 or it can form on carbon 3. So we're going to put the blue H over on carbon 4 like this. And it's a good idea to go ahead and show it just to kind of help us keep track of what goes where. And we're going to end up generating this very stable, resonance stabilized secondary carbocation because that's going to be our most stable intermediate between the two options we just observed as far as where to put the carbocation. So we're going to have a little bit of resonance here, so that's why we've got our brackets drawn. And we're going to take our pi bond and go like this. And so now we have this carbocation here. And then basically the nucleophilic attack we talked about earlier, chlorine, which is now floating off in space somewhere, is just going to come in and bond to wherever that carbocation is. So keep track of where that initial H went. And you'll see why here in a minute. And wherever the carbocation is, that's where we can show the chlorine. And we're going to ignore chirality for now. We're going to call this product the 1,2 kinetic product, and we're going to call this one the 1,4 thermo. Now where those numbers come from is just the relation of the H and the Cl, the two things that we're adding, to each other. So when they're right next to each other, we're going to call it the 1,2. And when they're a few atoms apart, we'll call it the 1,4 thermo. Now everything that we did with this pi bond here, we're also going to react with this pi bond here. So let's head to the next page, and we'll do our proton transfer first, like this. Of course, that's going to pop off this chlorine, like that. And again, our two carbocation choices here are going to be between 1 and 2. The more stable carbocation is going to be on carbon 2 when we add the blue H to carbon 1. So just go ahead and fill that in everywhere applicable. And then of course, this is going to be a very stable tertiary resonance stabilized carbocation. So we'll go ahead and show this pi bond flipping like so. And that's going to generate this intermediate right here. And then ultimately wherever you see those carbocations, that's where we're going to fill in our chlorine like that. And again, we're going to ignore chirality for now. So in this particular case, this is going to be our 1,2 kinetic because the blue H and the Cl are right next to each other. And this is going to be your 1,4 thermo because they are a few positions apart. Now, usually you'll have some kind of questions involving stability. So we kind of have 4 total products in 2 sets of 2. This will be one set of products. This will be the other set of products. And the way we're going to determine the major product in an asymmetric diene such as this is we're going to go back and look at the stability of the carbocations that we came up with in our intermediates. So here we've got a secondary resonating back and forth between a primary, and that's when we're using this pi bond. And on this molecule over here, when we're using this pi bond, we end up with a tertiary resonating back and forth between a secondary. And a 3,2 is always going to beat out a 2,1. So because this set of intermediates is more stable, that means this set of products is going to be our major set of products for this particular reaction. If you found this video helpful but need a little more practice or in-depth explanation, you can find the full length version over at orgogoat.com. Please like, comment, and subscribe to help our videos find more students like you, and tell a friend. And if you're interested in private tutoring or you want a concept explained that you don't see on our YouTube page, shoot me an email at orgogoat@yahoo.com.